So, welcome back, ladies and gentlemen, and I'm really excited about this next segment of the show because just last week, the science world, and let's face it, the whole world was kind of falling over themselves backwards because for the first time ever, we had seen an image of a black hole. Now, you know how I love to try and bring on the best guests to cover these biggest stories. Well, just out of the blue, out of a black hole, pardon the pun, there was an email landed on my desk, and it just happened to come from Dr. Brian Keating, an astrophysicist at the University of California in San Diego. And he was saying to me he would like to come on and discuss this discovery. So I'm really pleased to have Brian here with me. He's also the author of the book Losing the Nobel Prize. Now, I've spoke to Brian before, but I will get him to recap his story before we get to this amazing image. I've really been blown away by it. And I know people out there question everything when it comes to what we're seeing in space. However, I'm really enthusiastic about this. I know Brian is too. And not only that, but 2019 is going to be a really, really big year. It's a significant year, especially when it comes to gravity. So, Brian, welcome back to the show, sir. It's great to have you here, man.
Kev, I love hearing your voice and I love speaking to your listeners.
Oh, thank you so much, sir. And of course, is this not a very special date for you? Is this like the anniversary of the book?
Yeah, it's the anniversary of my first book, and perhaps it'll be my only one. I can't say for sure. So it's quite an exciting time to think that it's been tens of thousands of people. It's been at least in the U.S. It's been a kind of top 1% book across all categories. So I couldn't be. I never would have expected that if you told me that 2 or 3 years ago when I was deep into the manic flavor of typing and trying to get it out and get it on deadline. Never would have guessed it.
And of course,
So.
not many people can say that their book has been read down at the South Pole, right?
Yeah, that's right. Yeah, my book's been read at the South Pole. I'm trying to get it to go to space, but that's going to be a little tough. Although I do have two amazing young women, astronauts. One who went to my alma mater, Brown University, and she's going to be in space pretty soon on the space station. And then UC San Diego alumna, she is also going to be up there in the space station not too long from now. So I'm hoping to sneak up a copy. Maybe it'll only be in electronic format. That's a lot lighter. It costs a lot of money to escape the surly bonds of Earth's gravity.
Absolutely. Or just maybe sneak one into Elon's suitcase before he takes off for Mars. That might be a nice trick to play on him. But Brian,
That's
let's go back and find out this losing the Nobel Prize. I mean, not many people really can claim to that. And of course, the title of your book, and it was all because of a famous experiment. Now, can you kind of take us through how I know it's a big story, there's lots of elements to it, but as best you can, kind of tell the listeners what led to the losing of the Nobel Prize.
Yeah. So early on in my career, I'd wanted to, maybe more than anything, create an experiment that would garner me a glimpse back to the very beginning of time. And along the way, if I were successful, I was under no misapprehension that that discovery would be called the greatest discovery of all time, perhaps, and it would certainly warrant a Nobel Prize. The thing I didn't know is that it would be possible to do it or not, because the signals that we're talking about here really give rise to the. I mean, microscopic doesn't quite capture how minute the signals are, and so I knew it was a huge long shot. And yet in 2014, by the time I had kind of unceremoniously been kicked out of the leadership of the experiment that I sired, called BICEP, down at the South Pole, which I describe in the Physics and Space Sciences, Center for Astrophysics, rather, they made an announcement that we, the BICEP team, had discovered the first whispers of what was called cosmic inflation. And I shouldn't really maybe even say whisper, because the birth of the universe was such a violent event, such a mind-shattering event taking place in such a minute fraction of time that it was really, as in the words of Lawrence Krauss, who's a very well-known popularizer and scientist himself, he said it was perhaps the greatest discovery of all time, or it had increased human knowledge more than all discoveries prior to that date. So it was clear that we were all going to win Nobel Prizes, perhaps, except for me, because I had been, sort of intentionally dismissed from the leadership role in the team that I had once played prior to that event. So we ended up making this announcement and later having to recant and retract our interpretation and essentially disconfirm our hypothesis. Not that we made a blunder, not that we made a mistake and left the lens cap on the telescope or something foolish like that. No, instead, what we had done is detected an astronomical signal, a signal from our galaxy instead of a signal from the birth of the universe. And this astronomical signal, this galactic signal, was comprised of nothing more than dust. I'll sprinkle some dust. I brought some dust with me. No, I always have dust on hand, as do almost all of us, because literally that's what most things in our local universe are made of: dust, rocks, chunks of pre-exploded stars in our solar system and neighborhood. So it was very disheartening to lose the Nobel Prize in that way, to come so close to grasping this golden ring that I had aspired to as the greatest accomplishment I could ever achieve, or so I thought. And then later, the process of discovery that I went through to realize that there was much more to life than winning, a golden medallion engraved with the idolatrous perspective of Alfred Nobel. And now I'm happy to say I'm Nobel lust free, and I'm loving it.
No, absolutely, man. You do look you look extremely happy. I was saying to you before we kind of started recording here. You look like you're glowing, brother. You really do. And no wonder, because the world that you move in right now, so much great news is upon us. And I really want to get into this because this black hole image that has come out, I mean, absolutely spectacular. Talk us through all of that and what you know about it, Brian.
Yeah, so it was a great achievement to see this discovery announced on April 10th, just about 2 weeks ago, exactly. This announcement came, sort of not terribly surprising in that there had been a press conference announced, weeks before that. In the community, we knew that, I mean, the name of the telescope that made the discovery, it's actually not a single device. It's not a single telescope the way BICEP was a single telescope. No, instead, the Event Horizon Telescope is a network of about a dozen or so telescopes scattered around the Earth. And by putting together that many telescopes that far apart, these are radio telescopes, not too dissimilar from the BICEP kind of wavelength of interest. These are 2 millimeters to a centimeter or so in length. And they're very long, versions of infrared or visible light wavelengths. And these photons have been traveling from this black hole, several millions of light years away, and traveling from a galaxy called what we call M87. They probably call it something else. It's their version of the Milky Way, if anybody exists there. And this galaxy has at its heart a massive black hole. And this massive black hole is many, many times the mass of our sun, and perhaps many, many times the mass of the black hole that's at the center of our star. So this is kind of just an amazing discovery in terms of what the implications are for science. It really meant a confirmation and a discovery of something that had been predicted for 100 years, more than 100 years, that the consequences of Einstein's theory of relativity would result in such a phenomenon was really discovered or predicted in 1917 by Carl Schwarzschild and other people. But to see it verified in your lifetime is just such a spectacular feeling to have. So you're right. I am glowing like a black hole. I am the fact that you can actually see invisible signals and invisible objects like black holes, the most mysterious, enigmatic entities in the universe, is just an incredible feat to have been witness to. I didn't play any role in it. I know many members of the team. I'm very happy and proud of them. And it also kind of gave a lesson in the politics of science, which I'm very much more familiar with and happy to talk about as well.
No, absolutely. And one of the things I've come across most in my time talking about this is because to understand a black hole, we're told that nothing, even light, cannot escape this. So I think some people out there are kind of, puffing their cheeks and going, oh, yeah, whatever, image of a black hole. How can you take an image of something where light can't escape it? And it's not light per se because it's radio frequency, isn't it? It's gamma and X-rays. And it's the fact that all of these telescopes, I believe it's 8, they've been recording these signals, haven't they?
Yeah, they've been working for years. The signals start off, in all different wavelengths as the black hole gobbles up material. So you're right, you're not actually seeing the black hole. That's why it's not called the Black Hole Telescope. It's called the Event Horizon Telescope. So it is somewhat of a misnomer to think of this famous Eye of Sauron image that you have as really representing the actual shadow of the black hole itself. It's true we cannot see the black hole. It gobbles up all the light and all the matter that falls into it once it gets closer than the event horizon. So the event horizon is something which I could tell you in kilometers. It's 40 billion kilometers. That really doesn't give you a great a great kind of distance feeling. I could say it in miles or whatever, but really it's more akin to we talk about things in terms of light seconds or light minutes and how long it takes light to traverse the distance if light could do so without getting sucked up and gobbled up by this black hole. So what you're actually witnessing is, this massive object. This is about 7 billion times the mass of our sun, and it's concentrated into an area, a few times the diameter of our solar system. So what you're seeing is a shadow of something, which is not too dissimilar. If you were to say, well, this is crazy to say, but imagine you say, well, like we can detect during an eclipse. We can detect, the existence of the moon. Let's say you couldn't see the moon any other time except when it was blocking out the sun. Let's just live in an alternate universe for a second. That would happen very rarely. You need special equipment, and in fact, this was also the confirming feature that led to the proof of Einstein's theory of relativity, which had as a consequence its manifestation of black holes. And it turns out 1919 was the year that this happened. For the first time, the eclipse was observed of the total eclipse of the sun. And that led to the confirmation and instant celebrity of Albert Einstein. And we're in the 100th anniversary of that. I hope we can talk about that. And so imagine you can detect a lot from a shadow, in other words. So you can learn a lot about the sun's properties, its corona, its streamers, et cetera. I witnessed my first total solar eclipse in 2017 and hope to witness another one in July from Chile. And it's quite startling to know how about the shadows, lurking in the shadows. It's kind of a beautiful metaphor for what a lot of we do in science, and going back to Plato himself.
The way I've had it described to me, and you could correct me if I'm wrong here because you would know far better, but it's almost as if we can look at something like CERN, the particle collider, and then you've got this big accretion disk, right, where things are spinning around close to the speed of light as they're tumbling their way into this black hole. And is that what gives rise then to the gamma and X-rays that have been coming off?
Yeah, exactly. And the radio waves. So you get this heating effect when you accelerate matter and you compress it, and there's frictional heating of debris of the stellar corpses that are so unfortunate to get within the event horizon's distance. And so the black hole has been producing this jet of explosive activity, and that was observed maybe even 100 years ago optically. But there was nowhere near even the Hubble telescope. Kev, the thing to appreciate is that even the Hubble telescope, which is about 5 or so meters or 4 meters on a side, the diameter of the Hubble telescope, and it's in space. It's actually 3 meters, sorry, and it's in space. This telescope, with its amazing vantage point, was still thousands of times less precise, if you will. It would not be able to take an optical image of this telescope with a resolution even approaching 1,000 times as good as the resolution that the Event Horizon Telescope produced. And that's because these 8 telescopes were scattered about basically the diameter of the Earth almost. And so you can synthesize a telescope that's thousands of meters in diameter, thousands of kilometers in diameter. So millions of times bigger than the Hubble telescope. And that gives you the ability to resolve things many, many times finer than the optical power of even the most powerful optical telescope in the solar system, which is the Hubble telescope.
I read something and it really kind of struck a chord with me because we hear about the singularity at the center of these black holes, where basically the laws of physics as we know it, they're basically suspended. And then we also hear similar language about the time or the instance of the Big Bang. Everything came out of a singularity. Now, there was kind of a hypothesis out there, what's on the other side of a black hole? Do we come from a black hole singularity ourselves? Is it wormholes? I'm taking you into the land of speculation here, obviously, Brian, but it's the language they use, and that I think that's what sets the imagination wild.
Yeah, exactly. So there's a lot to unpack in that question that you have, but it's very perceptive because there is and was noted very many features by the late great Stephen Hawking. So we're more than a year since he passed away, and this his discoveries in both the theory of black holes, where he famously showed that black holes aren't exactly black. They're not even themselves, even within the event horizon. From the beyond the event horizon, they can actually radiate what's called Hawking radiation. And of course, this radiation is way too faint to ever detect by any telescope, even the Event Horizon Telescope. It's many trillions of times fainter, and so will not likely be detected in any time in the future. But what Hawking realized is that the radiation, the properties of the universe when it came into existence, shared many features, and one of which is sort of this singularity, this boundary wherein beyond which you receive no more information, and that has to do with the structure of space-time itself and how signals can propagate no faster than the speed of light. And so, in the early parts of the universe's existence, if indeed the universe began with a singular beginning, the universe would have experienced conditions very much like a black hole, or I like to think of it almost like a white hole, and everything rushing out from a point or from a finite region of space-time. And that would be a phenomenal thing to be able to witness. And we are searching for exactly the analog of radiation from the event horizon of the universe when we search for these gravitational waves in the Big Bang's first moments, using telescopes like BICEP. So there's a great many connections, and not the least of which is the work of Stephen Hawking, who contributed to both our understanding of black hole structure and how the universe may have itself originated in a singularity, very much like the singularity expected to be present at the surface of at the center of a black hole, if you will.
That is fascinating, because I can see the connections almost between searching for the ripples, the gravitational ripples from the Big Bang, and what's happening here on that's almost the macro level, and this black hole's like the micro level. It really is. That's why you're the best person to really come and speak to all of this. And of course, 2019, special year for physics, right? 100-year anniversary, Brian?
Yes, that's right. So, as I said, back in 1914 or so, Einstein really finalized his theory. 1912 to 1914, Einstein finalized his general theory of relativity, which was really based on correcting some of the flaws that were noted in Newton's laws of gravitation. So remember, Newton's laws of gravitation led to the inverse calculation, precise calculation of the planets, etc. And yet there were curious lacunae, there were problems with Newton's laws. And one of them was that the orbit of the planet Mercury, the closest to the sun, the one closest to feel its gravitational pull, was not behaving the way that Newton's laws would have predicted. Einstein knew about this, and he set out to really retrodict what was the cause of this curious advance of the what's called the perihelion of Mercury, which is a minute effect. We're talking, basically much smaller than a human hair held at arm's length. You're talking about, humans' hairs held over out over football fields length. So it's just incredible, tiny, minute fractions of angles that were being missed in Newton's theory. So Newton's theory was spectacular, and yet it was known for a while that Newton's theories must be missing something. Einstein said basically correct these flaws in Newton's theory, and did so and made a prediction that agreed with Newton's theory. And that was phenomenal. The problem was that it was basically an explanation of a previous phenomenon. In other words, he already knew the answer before he started off in making this prediction. And so there's always a danger of what's called confirmation bias, where you set out to prove something, and lo and behold, you prove it. Now, in Einstein's case, he was correct. Later on, Newton had also predicted how light would bend as it moved around the sun. And Einstein knew that he could actually make a prediction, which later turned out to be needed verification during a total solar eclipse. The confluence of technology of photographic plates, of telescopes, and travel, etc. So what ended up happening is very interesting. Einstein really proposed that this theory of relativity could be definitively proven in 1914, which I'll remind you is 9 years only after his discovery of many effects, and not the least of which was the E equals mc squared, his famous equation relating matter and energy. He did that, and he received a lot of attention, but he didn't receive the coveted Nobel Prize that he wanted so badly himself. He had a Nobel lust driven as much as I did, and that might be the only way that we're similar in any way. But at any rate, Einstein was not really, people didn't believe in the power of his ideas until long after the discovery of E equals mc squared. And it took until 1914. He said, look, there's going to be an eclipse, and it'll be visible from Prussia, from Germany, from Western Russia, etc. And we should set off on an eclipse expedition, and astronomers should observe it, and they could confirm that I'm right once and for all, and that general relativity, this phenomenal bending of space-time itself and warping of space by matter, you can prove it. Well, your history, I'm sure, and you'll know that 1914 was not a good time to do an expedition in Prussia, and the Prussian Austrian Empire. They were experiencing some upheaval. World War I was raging, and so the only astronomers who got sent to Crimea, of all places, they were kidnapped and abducted, and they weren't allowed to complete their observations. So the world had to wait until 1919, when the war was over, and there was another eclipse visible, this time visible from two stations on Earth where astronomers could be located. One was in Brazil and one was in Africa. And they did it. They actually, a team led by Sir Arthur Eddington, measured the deflection of light by the sun with exactly the exact predictions that Einstein had claimed, 5 years earlier at that time. So by that time, Einstein became famous. He became a worldwide celebrity overnight. The eclipse occurred, I believe, in November of 1919. He was on the front page of the New York Times a couple of days later, and it was claimed that only 3 people on Earth could probably understand his theory, and it made him such a celebrity that his Nobel Prize resulted basically at essentially the next possible opportunity, which turned out to be his winning the 1921 Nobel Prize. And that though wasn't awarded for his theory of relativity, either E equals mc squared or anything else, but rather it was sort of his service in understanding a previously discovered effect by a German physicist. So it really tickles me that these two phenomena, partially the discovery of black holes and partially the eclipse that happened to judiciously be located in a place fortuitously to be observed by astronomers of that time, and those two serendipitous factors conspired together and really revolutionized our understanding of reality, and not just arcane aspects of microscopic physics. So well, it's a wonderful year that this discovery could take place within.
To tip our hat again to Einstein himself, we could almost argue it's spooky action at a temporal distance.
Yeah, in some ways. I mean, he had a lot of good ideas. He had a lot of mistakes. And I think he is, he's the only scientist that I would say, most people don't really recognize, say James Clerk Maxwell, most people, or they won't recognize, the discoveries of Bohr or Schrodinger. If they know any physicist, it's Einstein. And the problem with that is that he kind of becomes an emblem for how physics is actually done. And to give him his due, he really was perhaps one of the greatest minds of all time. But the thing I always like to point out is that he made some spectacular mistakes. And those mistakes really give him a human character. The day after, a couple days after he died, there was a magazine, Time magazine in the U.S., or actually a cartoon in the U.S., and it showed a picture of the Earth from space, and it had a huge sign on it and said, Einstein lived here. And it really kind of exemplifies how important he was. He was Time magazine's man of the century. And you can't really think of any other physicist before or since who had such a great impact on our notions of life and reality. And as I say, he made a number of blunders, including, as you made a tip to, the spooky action at a distance, which was basically incorrect.
And what do you think of Nikola Tesla? Because I really hear a lot about him, some of his work. I think that was another genius, only it was a path not taken.
Yeah, so he had many ideas. He was primarily known for his inventiveness and his creativity in the laboratory and building things. Experimentalist myself, I actually salute those notions of experiment being as important as theory. Although we tend to give credit to theorists nowadays. Ironically, in the past it wasn't so. But yes, you're right. I think Tesla made foundational discoveries in the natural sciences, and some of those turned out to have great practical applications.
And what is Brian Keating working on these days? Because, I thought you had it tough down at the South Pole, but nothing in comparison to Crimea and all that stuff you
Yeah.
described a moment ago. Tell me you're somewhere better now.
Yeah, so right now the bicep project continues. I am really not as involved with it as I had been in the past. Primarily at this time out of choosing, really, that I am more than fully committed to technical progress via my leadership in what's called the Simons Observatory, which is a project of about 258 scientists around the world. And I'm the director of this observatory, and you can find out more about it at simonsobservatory.org here in the U.S. And there's some wonderful videos, and we have a YouTube channel, et cetera. And that's been one of the greatest privileges of my life to be the leader of this dynamic, brilliant group of scientists. From age 18 to we have someone who's almost 80 on the team, and to be involved with them from all backgrounds, all genders, all cultures, on all 7 continents. it's such a spectacular honor, and it really, as I say in the book, if we should happen to make a discovery that is one for the ages, I really like the fact that there's so many people, because I don't think the credit should go to any one individual. This discovery by the Event Horizon team was phenomenal, and I think it's sort of incorrect, or it's anachronistic, to want to always find a single individual, the hero on his journey, and he goes to the other world and comes back with the elixir and shows the world a new path. I think that's really out of place. It makes for great, movies and sci-fi movies, but I think it's pretty much an overused trope in science that's actually the case. Unfortunately, that's one of the negative consequences of Einstein, that he really did a lot of stuff by himself. Not all of it, and he died, without realizing his greatest dream of a theory of everything. But even with this Event Horizon discovery, you may realize, and your listeners may remember, the first minutes after it came out, there was this viral picture of this young scientist, happens to be a woman, and she was shown in front of a picture, and the caption was, she made the algorithm that made this discovery. And so many people, and my friends that are on the team, and other people, were really upset about this. And they weren't upset at her. It was the being upset at the narrative that the media had spun up. That it was, for a change, it was nice to have a woman as the kind of the celebratory figure. But it gave a lot of short shrift to the hundreds of people that had built the instrument, that had observed from the South Pole to Chile, everywhere in between, and what that meant for science is that, okay, here we go again. And in the U.S. there were Congress people celebrating her and claiming her as the leader of the project, and it put a lot of pressure on her. And it really distorted, kind of the actual way the science. And she had nothing to do with it. It was just an innocent tweet or something that had gotten put out by MIT, and then that got spun up by a great many institutions. So it was very unfortunate. I had a lot of disgruntled emails, people saying this must remind you exactly of Bicep 2. In some ways, it did, but in other ways, it didn't. And I think the world clamors for the hero or the heroine. But that's simply not the way that science is done. It's a distortion and misrepresentation. And part of that is contributed by the Nobel Prize, as I point out in the book. This has been perpetuated now for 117 years, that science is done by lone individuals working in isolation that are finally struck by genius. And what could be a worse message to send to your kids, right? Oh, well, you can be famous and win this $1 million prize and be world renowned as long as genius strikes you. So just plan on that happening. It kind of belies all the hard work and dedication and teamwork, collaboration, and international partnership that is required for science nowadays.
It's quite funny you bring that up because next month, sorry, I'm going to be joined by Geordie Rose. And he's obviously kind of coined as the guy who created the first quantum computer. But you're right, because it's a team of people. And I'm sure Geordie himself would be the first to point out, that it's not just him that brought this machine into the world. So, yeah, it is good that we remember that these are huge teams at times. Like
That's
over,
right.
over at CERN, thousands of scientists working on individual programs. So, yeah, it's good that you point that out. It really is. But I'm excited just as a layman. Okay, I mean, you're in these fields, but we've had LIGO, that kind of discovery. We've got the black hole that we've been talking about here. Seems like Elon Musk and other companies are taking us into space cheaper and faster all the time. We've got the James Webb Telescope, I believe that's coming soon. It's a really exciting time, Brian.
Yeah, it's really enjoying a golden age of astronomy. And, I noted that recently that there are more books kind of in production or have come out recently about two subjects, either astronomy, slash quantum mechanics. There's like 7 books that have come out just a year or will come out this year. Sean Carroll, a friend of mine, is coming out with a book. There are many other books that have come out in the last year. And it's just startling to think that, this 110-year-old subject is enjoying this huge popularity and renaissance, not just amongst, kind of, brainiac wonks like myself, but really in the public. These are public, popular level books. And it's exciting, it's gratifying to see the public so engaged and so excited as you are. And I think I know the reason why. Both in cosmology and in quantum physics, there is no room for the political. And people, Kev, I know you don't get super political, but, people are sick of politics. I mean, look, if you think it's really important that you stay on top of every single detail about what your prime minister, I mean, it's important to be educated citizen. I'm not going to deny that. But how important is it really that me, some professor in California, that I really am up to date on the minute by minute updates of Congress or some political aspirant for president? I really don't care, and I don't matter. I really don't matter when it comes to that. I'm one voice. But in science, if you do something or discover something or touch somebody with an inspiration, that can lead to their career. It could lead to their career for their children, and I just think it's so spectacular. And I love the fact that science is apolitical, and I hate it when people ask me or talk about and want to say, what do you think about this person's view on that? Or, the worst is global warming. I mean, it's impossible not for me as a cosmologist to not be asked at a public talk in front of hundreds of people. What do you think about global? Who cares what I think about global? I'm not a climate scientist. I'm a physicist. I understand the physics, better than most any layperson. But I'm not an expert. And I said, look, I hope you get somebody here, and I hope he or she will tell you all about the climate and change and what's happened, and be apolitical about it, and that's important. And then I hope when you ask him or her about a black hole event horizon, that they tell you they don't know the first thing about it, and they should defer to somebody like me. And that is what I think scientists should do. They should stay out of politics beyond being, involved civically. And I think that gives people, the general public, just so much more of a breath of fresh air to have a politics-free zone. I'm sorry for the rant, but I do feel like we get so caught up in the minutia of politics, and that's part of the reason of the appeal of inspiring popular science books. You can lose yourself and be detached for a moment where the political won't enter into your mind.
Oh, I'm with you, dude. You're preaching to the choir here because I realized a long time ago, like you say, we don't matter in the political game. And, to speak about that puts you in one box or another, and you just end up in silly, pointless arguments over something that we can't affect. And I always point out to people, and it's great that we can look to science, CERN, the International Space Station, you name it. These governments go to war. But when it comes to science, there are no borders. It's all about
Right.
ideas, it's about experimentation, and it's about taking us forward. So, I think as a whole, humanity should look at the scientific field and say, look, We all cooperate. We all get along, and you know what? It works.
Yeah, exactly. And that's the thing, it's like what inspires people. I always say, there's no Republican constellation, there's no labor planet, right? So we should really take pleasure in that, and there's room for that. And people didn't used to be, such political animals and junkies. And I think that's what, politics is important. Look, if we don't have a government, if we don't have, a peaceful society with the rule of law and a civilized society, I wouldn't be able to do what I do. I mean, I serve at the pleasure of the people of the United States, in some sense, who pay my salary, or private foundations that pay my salary. But I'm a public employee of the state of California. And so I need a government. I love I'm friends with them. I give them tours of our observatory. I do whatever I can, but I ask them to stay out of my science, and I'll stay out of their politics.
Very, very well said, sir. So we've got about 5 minutes or so before I let you go. Anything, any kind of messages, anything you're looking forward to later on in the year coming from science? Are we looking at any kind of other big announcements coming?
Yeah, I think, well, one thing that's going to be coming up in the United States, and to some degree in Europe too, is we're planning for the next entire decade of the future of astronomy. So we're assembling in 1990 for this 2020 report, aptly named, we're trying to plan out all the strategy for how we should deploy national resources. So for NASA, the Department of Energy, private corporations, things like SpaceX, et cetera, as you mentioned. And we're trying to orchestrate, what should be the division of labor and topics. And I get to read some of these proposals, and I'm leading some myself with my colleagues on the Simons Observatory. And that's to really scope out what could we, no pun intended, what can we do to advance astronomy, the search for habitable worlds beyond our solar system, the search for the census, the cosmic census of how many black holes are there, how many things like supernova will go off, and how do we study the mysterious forces of nature that are dominating. We're a very small part of the universe. The matter that we're made up of, protons, neutrons, in my case, croutons. I love to eat. And these things are very minute. Less than 4% of the observable universe's energy is contained in the mass energy of those entities that I just mentioned. The rest is totally mysterious. Dark energy, dark matter. We almost have. It wouldn't be a far stretch to say we're basically where we were with respect to gravity in the time of Newton. When it comes to understanding dark energy and dark matter. So we need to understand those. And how do you go about doing that? Well, you have to marshal your forces to build big experiments, to have giant supercomputers at work, and to build theoretical tools and frameworks and train the next generation of scientists to do that. And so we get to be a part of that. And that's one of the great many blessings I'm looking forward to this year, is really understanding what is it going to take to move human knowledge even farther into the future in astronomy in the decade from 2020 to 2030. And that, I don't know, I might be retired at the end of that,
Well,
right?
I love the whole quantum stuff. I've always loved watching presentations on that, but recently listened to something. It was Leonard Susskind, his name is. And he was talking about,
Stanford. Yes, I
yeah,
know him well.
quantum gravity, and it was
Yeah.
mind blowing. But he seems to think this could take us a lot closer to, that grand theory, that
Yeah,
unified theory.
yeah, exactly. The understanding of gravity at the quantum realm is really a holy grail that, as I said, eluded Einstein himself. But by the same token, we have access to technology and computing power that Einstein could never really have dreamed of. And I am hoping that the combination of quantum computing, which hopefully we can talk about another time, I will put you in touch with some great experts here that are really at the forefront of testing what are called Bell's inequalities, and these are aspects of quantum mechanics that really appeared mysterious and spooky to Einstein and left him perennially unsatisfied. So what I would love to do is to recommend a couple of guests that have built and been featured in the Nova episode recently on PBS here in the United States, and that was to really test Einstein's spookiness and see what is the nature of reality at the quantum level.
Wow, almost speechless there. I really am, but I really thank you for your time today, Brian. I urge everyone to check out the book, Losing the Nobel Prize. You can head on over to www.briankeating.com. Any other places where people can follow you? I know you're active on the old anti-social media, right?
That's right, anti-socialist. Yes, on Twitter, I'm Dr. Brian Keating, and on Instagram, YouTube. I have a YouTube channel now. Please subscribe to that. And doing a lot of interviews for the Arthur C. Clarke Center for Human Imagination. We have a wonderful podcast. You can subscribe there on my on my YouTube channel, or find on my website, briankeating.com.
You have some wonderful scientists visiting the Arthur C. Clarke Center, I must admit. Very envious of some of the people you get to speak to, Brian.
Yes, it is. I feel so fortunate both to be able to kind of resonate a little bit with Sir Arthur C. Clarke, late great genius who really melded science fact, science fiction better than almost anybody in history.
Well, I
But then I get
sometimes play one of his little videos, and he was describing what the future would be. And, you know, you can basically look at everything he predicted. It's almost as if
yeah,
he was prophetic. Nostradamus
what?
didn't have a patch on this dude.
Yeah, exactly. I think it's just phenomenal what he was able to accomplish. And so, yeah, we're really honored to be able to use his name and his likeness, thanks to the Arthur Clarke Foundation. And then we get to interview these brilliant scientists, young and old, male and female, from around the world. I did one last week with Annalee Newitz, who's a brilliant sci-fi author and also science and nonfiction author. And you can find that on my YouTube channel, Dr. Brian Keating, as well.
Awesome stuff. So I will let you get back to your day, sir. But ladies and gentlemen, please check out the phenomenal, and you know, Arthur C. Clarke has got a phenomenal member of staff right there. I tell you, check him out, Dr. Brian Keating, www.briankeating.com. Losing the Nobel Prize, and I'm sure we'll hook up again soon because so much happening out there in space. Thanks very much, Brian.
Thank you, Kev. Have a great day.